So I want to do a couple of conditional probability examples involving Gaussians. Okay. So first example I want to do is x and y are jointly Gaussian with zero mean, unit variance, and correlation coefficient that is not equal to 0, right? We talked about correlation coefficient back in lecture 45, and also again when we introduced what the concept was for general random variables, right? So we found out that the joint Gaussian PDF was the following, just simplifying out all the zeros and ones makes life a little bit easier. So I'm just writing down what we learned. Okay. So this is a little bit messy. What I want to now know is what is the conditional PDF of y given x? Well, actually, I realized that I solved this explicitly in the previous lecture 45, right? So remember that at the time, I was going to just compute the marginal, right? So this was a slide from a few lectures ago where this was my joint PDF, and I wanted to compute just the marginal of x. I did the integration, I did the computation, and I came out with this and showed that the marginal x was indeed just a Gaussian with zero mean and variance 1, right? But as a byproduct of that, I realized actually that I also computed the conditional, right? This we showed was a Gaussian PDF that had certain mean and variance. So let me just write that down explicitly, right? So what I know is that the joint is equal to the marginal times the conditional, right? So here I found out that I had a joint Gaussian okay. The marginal of x, so here I'm just looking at x and this is going to be y given x. The marginal I found had mean 0 and variance 1. And I found the conditional was, and everything was Gaussian, right? So this was Gaussian. This is the nice thing about Gaussians is that when I take marginals and so on, everything is still Gaussian. So that I found out here that this guy here had mean rho x and had variance square root of 1 minus rho squared. Okay? And so I just want to pause for a second and mention what does this kind of mean, right? So remember that joint Gaussians have this kind of like, if I look at them like a topographical map, I have kind of like these equally probable contours that looks like ellipses, right? And so let's think about what happens in this case. So let's suppose that these are my kind of equiprobable ellipses, and rho not being equal to 0 means that these ellipses are kind of at some angle, okay? So individually, if I look at the marginals, it's like projecting this topographical map onto the x-axis or the y-axis, and I can see that everything should stay 0 mean, right? Because I've got half the probability above the axis and below the axis. So the marginals themselves are both 0 mean. But now it's like saying, okay, let me tell you that I got this value of x, right? Now what I see is that my equiprobable world is kind of shifted up, right? So my integral is going to look like a Gaussian that has a mean that is somewhere over here, right? And that mean, as I computed, was equal to rho x, right? So I have kind of like this offset of the mean that depends on whatever the value of x was, okay? Whereas if I were to project downwards, I get 0. If I were to say, okay, just normalize along this line, things are going to be clearly shifted upwards from 0 mean, right? And that's kind of what we showed, okay? So sometimes it's useful to know this kind of, conditional of a Gaussian is also Gaussian with a shifted mean. So that can come in handy. The other example I wanted to do relates to what's called maximum likelihood estimation. We're going to come back and talk about this in some detail. I think I already touched on it before, but let me do an example of this. So let's suppose that I'm trying to estimate the mean of a PDF, right? So the idea is, and this is very related again to real world machine learning and so on. So the idea is that we observe samples, right, from some distribution. And actually generating samples from a PDF is something I'm going to talk about towards the end of all these lessons. But that's really something that you do all the time in coding, right? In MATLAB, that's like saying, give me a Gaussian random number, I use rand to n, and I get some number x. So the idea here is that I am picking these samples from the underlying PDF that I don't exactly know, and we hypothesize that we come from some underlying PDF. Is basically the same, and that everything is independent. Okay, so now what I want to do is basically maximize the probability that I saw these numbers given some parameters. These are, for example, like the parameters that make up the PDF. Right, I want to maximize this with respect to those parameters, right? So it's like saying, for example, let's make this really easy. Let's suppose that the underlying PDF is Gaussian, and that I know the variance, okay? And now the only thing I don't know is the mean. What would be my maximum likelihood estimate of the mean? So let's be specific. Let's suppose that the underlying PDF is Gaussian with unknown mean and known sigma squared. Okay, that is that the probability of x given that the mean is equal to mu is equal to this PDF. Okay. Well, if I assume that each of these data points is chosen independently, which is the assumption that you usually have to make, then I can say, okay, well, the joint PDF, and this is something we didn't really talk about yet, but you can imagine how this generalizes from 2 random variables to the n random variables that are basically the values that I picked, right? So then I can say the probability of this joint set of random variables, given that the mean is equal to mu, and here are the values. Well, I'm going to assume that each of these probabilities is independent, right? That picking x2 has nothing to do with how I picked x1, right? So I'm going to get the probability, or I'm going to get the product of all of these individual PDFs, and each of these is going to be equal to this number. Okay. And now what I want to do is I want to maximize this with respect to mu. How do I maximize something? I take the derivative and I set it equal to 0. Okay. Now this looks like kind of a painful thing to take the derivative of. So how to maximize with respect to mu, I would basically take the derivative and I'd set it equal to 0. Now the derivative of this thing is going to be a mess. But one thing to realize is that if I think about the log function, right, the log function looks like this. It's basically monotonic. And so this is x and this is log x. So the idea is that, the mu that maximizes some value z will also maximize log z. So the idea here is that instead of maximizing this nasty function, what I do is I take the log of it and maximize that. So this is called the log likelihood. So the log of this probability, well, the nice thing about taking the log is that the product turns into a sum, and then I take the log of this plus the log of that, right? So it's basically the sum of the log of this thing plus this is the log of what's in the exponent, right? Now, this thing I don't really care about because I'm going to take the derivative and set it equal to 0, right? So the derivative of this part is just a constant. What I get is the sum of the derivative of this with respect to mu, right? I'm going to get minus 2 xi minus mu times the derivative with respect to mu is minus 1, right? And so a bunch of stuff cancels. I want to set this equal to 0. What I get is then the sum of 1 over sigma squared xi minus mu equals 0, right? So sigma drops out. Mu is a constant. So then what I get is that the mu that I should use is the average of the x's, right? So this is like my best estimate of mu according to the maximum likelihood rule, right? So we'd estimate the mean of the distribution as just the average of the data that we saw, right? Which makes sense. And this is a maximum likelihood approach because if we were doing a more Bayesian approach to estimation, then I might have a prior distribution on mu that says, hey, I think that mu is already around 5, and so maybe I should bias my estimate to be some sort of an average between this part, which is agnostic about the value of mu, and the prior, which is something that I already have some existing knowledge about mu, right? So this is a version that's kind of like agnostic about the prior, and that's what maximum likelihood estimation is. We're going to come back to this concept of maximum likelihood versus Bayesian estimation in the context of parameter estimation in a few lectures. And so we're going to talk about estimation a little bit more before the class is done.